Hello and good morning. Today is April 2nd, Thursday. It is the last day before our spring break starts because tomorrow we have Cesar Chavez Day. And so no more streams and stuff for a whole week. Good morning, Dennis. How's it going? So no more streams for a whole week, and then we'll come back April 13th, Monday, and we'll start everything all over again. Make sure you're taking a look at the calendar. You can get the calendar from our website, of course, zphysics.net. Take a look, stay on top. We did a lab yesterday, or at least a virtual lab yesterday using the FET DC circuit kit, and we'll use that kit a little bit more as we talk about circuits in parallel today. Yesterday we did circuits in series. Let's see. Okay. So yesterday you should have seen some patterns based on how you arranged your resistors. Let's start with the PowerPoint. There we go. Resistors in series. Well, if you have two or more resistors that are in series, now you can tell that they are in series if they come one after the other. Okay, so as you can see in this model, you have resistor 1 and resistor 2. They're right after one another. The most important part is to visualize how the current is flowing in the system. So as the current is coming in, the same current goes through resistor 1 and 2, and therefore 1 and 2 must be in series. Okay? So if the same current goes through both of them, then they are in series. If for some reason the current is able to split off, if there's a secondary path or a detour or some kind after resistor 1, then they are no longer in series. So here, let me show you. So let's say you had current coming in like this, okay, where you had resistor 1 here, and of course you had your resistor 2, but if there's like another branch, imagine these are just roads, or different routes. Here's the 101 and here's the 5 freeway or something like that. So if there's a different route that you can take, then they are no longer in series. Okay, so this fork in the road makes all the difference. All right. Okay, so if the same current goes through them, then they are in series. And if they are in series, then a couple of things that you should have noticed from yesterday's lab experiment is that the voltages add up. Meaning whatever voltage you get at R1, and then whatever you get at R2, if you have a third one, whatever you get at the third one, R3, all of those should add up to the total, which is the battery. So the battery provides you with your voltage, and then the resistors kind of take it away. They dissipate the energy, converting it into heat. So imagine this circuit. Here's our simple circuit, right? Well, for this model, I'll just do 2 instead of 3 because that's a lot of drawing. So here's our circuit. We have resistor 1, resistor 2, R1, R2. Okay, and so you can imagine the battery being kind of like an elevator. Here's our elevator. Here's Dennis inside the elevator. All right, and so the battery boosts you up to some, high floor. So let's say if it was 10 volts, then you're now on the 10th volt floor, and you're up here now. Whoa. Okay, each resistor is like a set of staircases that you take downstairs. So this is resistor 1, and so you've fallen some amount of voltage. And so if the first one dropped V amount, then whatever's left, because there's only 2 resistors in this circuit, whatever's left will be dropped by the second resistor. And now you're, oops, that staircase is not very safe. Okay, now you're on the ground. So you're going to lose some more voltage. After losing all those, now you're on the ground floor. So what do? Well, you go back to the elevator to go back up again. Are we still going back to school on May 4th? Because I heard we're not going back. So the governor said no, but the school has not sent out the email yet. So wait for the school to give you an email. All right. So once you've fallen, you're now at the 0th floor, and you can go back onto the elevator ride and go back up again. So this is what's happening in our circuit, and you should have seen that the 2 voltages that you get, the voltage drops at R1 and R2, add up to your total voltage. Okay. All right, going back to the PowerPoint. Each individual voltages, as you can see here, if you want to find each individual voltage, like what is the voltage at R1, the first resistor? Well, you should have seen that the voltage there is actually the resistance times the current. Okay, take a look at your values, make sure they make sense. So the current times whatever resistor you have is the voltage drop at that point. So if I wanted to know what V2 is, the voltage at resistor 2, then it's just the current times resistor 2. Alright, and this leads us to this page, this formula here basically. The top is a derivation. This is how you derive the formula, but we can, once you derive it, you can take advantage of this equation here. Basically, Req, which is the equivalent resistance, meaning total, R total, equivalent resistance is equal to just the sum of all the resistors in series. So if you have 2 resistors in series, add them up, and that'll give you your total. Alright, so if you take a look at your numbers, R1, R2, R3, if you wanted R1, 2, 3, so let's go back. So that means in your lab, if you want R1, 2, 3, that's rec for all 3. So it's R1 if you know they're in series, of course. R2 plus R3 when in series. Okay. All right. So series is pretty simple. They're all just sum. They just add up. If you want total resistance, you add all the individuals up. Here's a quick example. Shall we class flow it? Nah. No, I'm not going to skip this one. Or should we? Let's class flow it. These school computers are so laggy. Well, make sure you're not running anything in the background. Yeah. So if you have nothing running in the background, you should be fine. All right. Well, anyway, it says calculate the equivalent resistance. So these are in series. The equivalent resistance, Req, would be 47 plus the 220. So let's see. How many volts was it? It was 12 volts. And 47, 220, like so. It's 47 ohms, 12 volts. So the total should be 47 plus the 220, which is 267 ohms. And if I wanted to, in the next question, in part B, it says find the current through R2. So the current through R2 is, if I look at my current flow diagram, there's only one current. Whatever comes out of the battery at the plus end, because the big line is the plus, will go through the first and then through second, and voila. Now, even though we say first and second, there really is no first and second. Both resistors kind of get the current at the same time. So everything happens as soon as you turn it on. You know, that's because of the domino effect we talked about. So in order for this 47 ohm resistor to get the current, a charge had to move forward. In order for that charge to move forward, the charge over here also had to move forward. The charge over here also had to move forward. The charge over here also had to move forward. So all of them, like a domino effect, moves forward like this. And so I2 should be equal to V2, or sorry, I2 should be equal to the total current, I total. And I total should be equal to the total voltage divided by the total resistance. Okay. Yeah. So the total voltage is 12 volts and the total resistance is 267. Notice how the current that goes through resistor 2 depends on resistor 1 as well, depends on the system. The amount of current that flows through your system depends on everything that is in the system. Okay, we know I2 is the I total. That's because whatever goes through resistor 2 is the same current that came out of the battery. It never split. So what is 12 divided by 267? It is 0.45 amps. Oh, I forgot a 0. 0.0, there we go. 0.045 amps. There. Okay. Next up is today's lesson, which is on parallel resistors. Okay. Let me go and draw some parallel resistors. So let's go and do resistors in parallel. And I'm going to draw it slightly different. So we'll start with the battery. We'll have resistor 1 here. And then I'll draw resistor 2 this way. Whoa, it's slanty. Okay. R1 and R2 are parallel resistors. Okay. So do we use that equation to find the missing I in the lab? Yeah. I total, wait, the missing I, the one at the bottom. So you have to put the ammeter in front of the battery. It says I through battery or something. Oh, the missing. Do we use that equation to find the missing I in the lab? There is no I1, 2, is there? No, there's only 1, 2, 3, and then there's a total at the bottom. Right? And the idea is that it is the same current in the entire system, so it doesn't matter what I you're talking about. So I1, I2, or I3, or the total current, they're all the same if you only have series resistors. Alright, so these are parallel resistors. Parallel has nothing to do with how they're oriented. It's not about being parallel lines. It's more to do with how current kind of splits up. So after the current comes into this junction here, this is a junction, a fork in the road. There we go. Junction. What is the function? Well, it's to split it up. So some of the current go through resistor 1. The rest will go through resistor 2. No, Kuya Casey, look at it. Look at this circuit right here. You see how the current comes into this point? There's a fork in the road, and now it splits up. So imagine two streams. It's like a big river that is, has lots of water coming, and then it goes into tiny little channels, two different ways. So, or you can look at it as like big giant blood vessels, and then the blood goes into little tiny capillaries. All right. So now we are splitting off from our main channel. So all these charges that are flowing will split up. However, after splitting up, it gets to this point right here. Okay. Now the other stuff, the other part of the current that went through R2 will eventually come around and meet up. So the fact that they split and meet again is why they are parallel. Okay, the fact that they split and then after going through the resistors they meet up again, they are parallel. Okay, but if there was another branch after R2, then R2 would no longer be parallel to R1. So if you skipped over, if you went a different direction, or if there's another resistor before you meet up again, then it's no longer in parallel. So in order for two resistors to be in parallel, after splitting off the current, they have to immediately combine again without going through any other channels or going through any other circuit element. All right. And this is our V. Going back to the PowerPoint. Here we can see how R1 and R2, of course, when you draw it side to side, it's really easy to know that they are in parallel, because that's the natural way to draw circuits in parallel. You can also draw it horizontally; they don't have to be vertical, as you'll see on the second lab. Go and go to your Canvas to download that one. The current splits up. And if you know what the voltage is, then you can easily find what the current is. Okay, so let's do some review. Resistors in parallel. Okay, resistors in parallel. Current splits up. Current splits such that I1 plus I2 plus ... equals I total. So the total current turns into little tiny bits. But the voltage remains the same. Voltage is the same. Meaning, whatever your total voltage is, V, the battery, must be equal to each resistor's voltage. Okay. This is the opposite of resistors in series. If you recall, in series resistors, where can I write this? In series resistors, we found that current is the same. So I total is equal to I1 is equal to I2 ... It's the voltage that adds up. V total is equal to V1 plus V2 ... So in series, voltage adds up. In parallel, current adds up. I thought Mr. Z said I won for a second. I won. Number 1. Okay. And the resistances add up really weird. And here's the derivation. If you want to find the equivalent resistance, the total resistance. Now I have it in this format, but I will give it to you slightly different. So see how it has inverse of resistance on the left side and the right side. So I'll kind of go one step further here and say that for resistors in parallel, rec, notice how in this equation, this form, I don't have an inverse on the left side. It's just rec as a whole is equal to, I'll just take the inverse of the right side, 1 over the sum of all the inverses. 1 over, 1 over. Red rover, red rover. Dot, dot, dot. So if you have more than 3, then you just keep going. So this is our general. This is our general case. There's also another one that I can give you. This is a specific case only for 2, so I call it rec for 2. It's like table for 2. Rec for 2, and it only works if you have 2 resistors. Do not try this with 3, because it involves more terms. And you can derive this if you want, just by finding common denominators. Essentially, it's product over sum. R1 times R2 over R1 plus R2. And I can go ahead and derive this using the general formula. We would, if I had 2 resistors, it would be R1 plus 1 over R1 plus 1 over R2, which is the same as 1 over R1, and we'll find common denominators. The common denominator is R1, R2. So for the first one, we'll have to multiply by R2 over R2. And for the second one, we will multiply by R1 over R1. Okay? This gives us common denominators, so we can add the bottom. So we have rec over here. We have 1 over 1 times R2 is R2 over R1 times R2 plus 1 times R1 is R1 over the product. Okay, add them up. So you get 1 over R1 plus R2 over R1 times R2. And then you take the inverse of that. That gives you, well, that gives you this. Product over sum. This is a shortcut only for 2, so table for 2 only. You know how when you go to a restaurant, if you're a walk-in and if it's only 2 people, usually you get to your seats a lot sooner than taking a whole party of like 10. Just saying. It's just a shortcut. Easier to accommodate. Right? Alright. So that's rec for 2. Let's see. The power equations are still the same. So power is power. Power is equal to IV. Whether you're in series or parallel doesn't really matter. Yesterday we got this equation, power equals IV, but here are 2 more. Using Ohm's law, we can actually get the other 2. Using Ohm's law, we can get the other 2. So let me show you how to get those other 2. Power, and we'll do a flippy when we come back. The last flippy. Power traditionally is equal to I times V, but of course we know that V is also equal to IR, and by substitution, if I put in IR in there, I get I times IR, which is equal to I squared R. Alright, that's number 2. And to get the other one, we want to substitute something else. So let's see. If V equals IR, then I is equal to V over R. And let's go and substitute V over R into I. This gives us V squared over R. So these are the other two power equations. Okay, you could use them, but for the lab, at least stick to P equals IV. P equals IV. Okay. Power also tells you the brightness of your light bulb. So at the bottom, there's some conceptual questions that you need to answer for your lab. You know, if they were brightness, how would if they were light bulbs, how would the brightness be affected, or something like to that order. Basically, look at the power of each resistor. Okay, whichever draws the most power is the brightest. And you can even use light bulbs instead of resistors in your circuit and see. Yeah. So anyway. And of course, the units, don't forget your units. Some of you who turned it in, check your units. I'm not sure if you had units. The units for power is watts, capital W. Yeah, we'll see this on Monday anyway. All right, now I will go ahead and pull up what we're going to do today. It's the lab parallel. So go to your canvas, and you should see this one here. Similar to yesterday, you can choose any 3 resistors, so do the same, so then you can actually see some pattern and some, do some analysis. So R1, R2, R3, whatever you used last time, keep them. But this time, connect them in parallel. Connect them in parallel. All right. Let's see, FET. So we'll go to the FET website, fet.colorado.edu, and then we'll go to physics, circuits, third one here, circuit construction kit, DC, virtual lab. All right. And I want to make a parallel, so we want 3 resistors in parallel. 1, 2, 3. Ooh. All right. Well, what else are you going to do? School's closed. And then connect them. So here's some wire. It's like Legos. Yeah, and it's so easy though, Giorgio. I think Kuya Casey did it in like 10 minutes and turned it in already. Oh, you don't see it on Canvas? That's weird. Let me publish it. There we go. Now you should see it. All right. And we want some more wires. So wire. And from here, I need to connect it to a battery. So let's get a battery. And then connect the wires. We need a full circuit, so, or a closed loop. And there we go. It's now moving. Let's use conventional flow. Well, I guess the other thing you can do, I can give you book assignments and like have you read books just like your other classes, and then have you do chapter summaries, do essays. Do you want to do that instead, Chris? Is that what you want? Read the physics book and do chapter summaries, and and write an essay about resistors. Yeah, let's do that instead, right? Is that better? Well, no, that's not how like that's no. We're gonna do like your history class or something. Let's do like a DBQ for physics, a document-based question for physics. Yeah, the book is in your Mastering Physics. It's on the left. It's called eText. We've been over this, Giorgio, since the beginning of the school. Yep. So make sure you use that. No essays, no DBQs. No, you don't get your cake and eat it too, right? Yeah, Christian. All right, let's. How about just Christian? You can do all the reading and the chapter summaries and the essays, while we just play with this simulator. Yeah, the Green Apple book. All right, similar to the last lab, let's go ahead and pull out our voltmeter. Use your probes at R1, R2, and you can find the voltages. Okay. Now, if you want to do R12, it would be at the start of 1 and then the end of 2. So if the top one is 1, the middle one is 2, and the third one is 3, it would be at the start of 1, or it doesn't matter which side is the start. So left side of 1 and then the right side of 2, like this. So crisscross applesauce. R13 would be blah blah blah, and it doesn't really matter. As you can see, the whole idea is that when they are in parallel, they have the same voltage. You're in the wrong class then. It is easy. I don't know. I don't know why you're saying it's hard. This is like the easiest lab we've ever done. You don't you don't even have to set it up. It's a simulator, and it gives you perfect numbers. There's no way of getting it wrong. And I'm actually like literally doing it for you. All you have to do is copy it. Of course, use your own values. So click on the resistor and then change the numbers to whatever you used yesterday. So it's a little different. Everyone should have like different things. Don't tell people what you're using, so you have different numbers. But the battery should be 30 volts. Oops, it's too much. Current. Well, current, we need to cut open a spot. So let's use the scissors, boom. And then we'll stick the current ammeter in there, and this will allow us to get all the currents. And you'll see that the currents are different. So let's cut it over here now. Whoa, that's too many cuts. Oh well. Cut. Let's fix it up again. We'll join that. Ooh. How should we do this? Cut. There we go. There we go. Alright, if I want the middle one, we've cut the middle one out. Cut the middle man. And then stick the ammeter in there. There we go. Now it goes through. So you can see that different amounts of current go through each resistor. Okay. Right. Questions at the bottom. If bulbs were connected in parallel, again, if you're dealing with light bulbs, look at the power values instead. Whichever has the higher power will be the brightest. Calculate all of your powers, P1, P2, P3, and then see which one's the brightest. How do you get P total? Chat, how would you get P total? What's your best guess? If I wanted the total power in the system, how could I get P total? There are two different ways. Of course, you can just do P tot, potato, is equal to the total current times the total voltage. It should also be the sum of all the powers, P1 plus P2 plus P3. It should be. And it doesn't matter what kind of circuit. Alright. Okay, yeah, your mastering physics is open. Make sure you work on your mastering physics over the spring break. You also have these two labs to work on. The first one is due this Saturday. The second one, the one from today, is due next Saturday. And that's all. So for the next 2 weeks, you should stay safe. Apparently, it's going to peak. So these next 2 weeks are the most dangerous of infection rates, etc. So try to stay home, do your physics. Physics will keep you busy. Physics will save your life. Just don't go outside. Why? Because a lot of people are not listening to the government, and they're doing whatever they want, spreading the disease. Are we able to email you if we have questions? Sure, why not? I'll be here. I go to work. Are you sure you go to work? Because unless you're, it's an essential business, everything else is shut down. Everything else is shut down. So, if you're like if it's an essential service, then yeah, wear your protective gear, wear a mask, wear gloves. It depends on the person, Chris. If it's you, I'll think about it. I'll flip a coin if it's Chris. If it's heads, I'll answer it. If it's tails, I won't. How's that? Is that fair? Why me? Well, it's because you don't like ClassFlow. That's why. ClassFlow is my favorite, and you don't like it, so that's why. All right. Now the mastering physics isn't due until a week after we come back, so we'll still have time once school starts again to ask questions also. So it's not required that you finish your mastering physics over the break, but it is required that you finish your 2 labs, one this Saturday and another one next Saturday. P12 is P1 plus P2. Oops, not R. It's for all labs. Power is just adds up scalarly, so you just add them up no matter what kind of system you have. Procrastination. I guess you can always procrastinate. But yeah. Anyway, stay safe. Stay home. Spread the word. It's gonna get ugly next 2 weeks. But as long as everyone does their part, at least in California, it's a lot better. It's just some other states where people are still like not listening. In other states, they're still trying to do get-togethers and assemblies and whatnot. So I think in California, it's a lot better than it is. But of course, our population is much higher, therefore, the numbers will look bad. And New York also has pretty high population, but at the same time, New York has less space than California. Yeah. Yep. Florida's pretty well. I guess currently like Louisiana and some other states are pretty bad. New Jersey. But I'm talking about like states who, currently they think they're fine because they're lower than the other states, but because they think they're fine, they're not, doing what they're supposed to be doing, and therefore they're only going to make it worse. But yeah. Now you should expect an email from the school giving you further details of what's going to happen. It's highly likely that the May 1st date will be extended. Yep. So anyway, I guess that's all. If you have any questions, just I'll be on chat. So I always do Q&A time after my ABC stream. So after like 12 o'clock, there's some Q&A time. You can always come in and join us there if you want. Yeah, RIP seniors. Tisk tisk. All right. Well, we're just gonna have to make the best of it. We can always do like a physics thing. Please do not let the school. Well, that's not our choice. Ah, Chapito. Yeah, I miss. Yeah, I definitely miss the classroom because right now, instead of doing this virtual lab, we'd be actually building a circuit. You know, it's unfortunate that classes like physics would suffer more just because our classes are much more hands-on and we get to actually build things and do things, and that's like the hardest adjustment is to figure out ways to teach similar things while doing it in the virtual world. I mean, what do you mean what he'll do? He's gonna go to college. It's he has better and better, brighter things ahead of him. High school is not the end of the world. High school is merely a stepping stone. And then once you get into college, you can have all sorts of fun. You can focus on whatever your life is going to be about. You'll see that you have more free time, but it is misleading. That's because they expect you to study and read and do all those things on your own, right? So just because you think you have less homework doesn't mean that it requires less work. It actually requires more work, and that more work needs to be done on your end. You have to find practice problems to do. You have to read the book. You have to do your chapter summaries to learn your content. I'm going to open up a Minecraft server or Roblox. Ah, yes. Yeah. Nice. All right. Well, I guess that is all. Thank you for tuning in. I'll see you next time.